Welcome back to the Deep Dive. Today, we are charting a course away from seeing AI coding assistants as, just a simple novelty tool.
That fun feature that just finishes your lines for you.
Exactly. We're moving into the far more serious and I think strategically vital world of AI as a governed contributing team member. We're working through a really fascinating collection of source material that's centered on how large platforms, particularly GitHub, are building these mechanisms to control and contextualize AI-generated code, not just for one developer, but across entire organizations.
And that's really the core of the matter, isn't it? Our mission today is to understand this new constitutional layer that's being embedded directly into software projects.
A constitutional layer, I like that.
Yeah. We're exploring how engineering teams are finally bridging that massive strategic gap between a giant generic language model, one trained on the entire public internet, and the highly specific, often kind of esoteric rules of their own unique enterprise code base.
Okay, let's unpack that. I think we have to start with the foundational challenge, which the sources we're looking at call the generic code problem. This is the friction point everyone hits first.
Oh, absolutely. It's a pain point that is instantly recognizable to, I think, every single early adopter of these AI tools. In their first forms, these assistants were fundamentally stateless.
Stateless. What do you mean by that?
They operated on what the sources call a cursor-centric model. So their visibility was just incredibly limited. It was, the file you had open, maybe 2 or 3 adjacent tabs, and that's about it.
So they were brilliant at syntax.
Brilliant at raw syntax. They could write a perfectly valid function that would compile with absolutely no errors.
But then you get this code that, while it's syntactically perfect, is what the research calls architecturally incoherent. It's sound on paper, but in context, it's meaningless, or worse.
Worse is right. I mean, consider this really common scenario. Your entire organization has spent months, maybe years, developing and mandating a custom internal fetch wrapper.
Right. And that wrapper is non-negotiable. It has to be used.
It has to be. Because it automatically injects critical features, right? Things like built-in telemetry, centralized logging, standardized error handling. All of that gets injected into every single network request.
But the base AI model, which was trained on millions of public GitHub repos, it sees a developer asking for an HTTP request, and what does it do?
It suggests the most popular library out there. It suggests Axios, or maybe just the raw, unsecured native fetch command.
So it's giving the most statistically probable answer from its training data.
Yes.
But it's the completely wrong answer for this company, for this project.
Exactly. The developer integrates Axios. The code works fine on their machine, but it fundamentally violates the company's non-negotiable security and architectural standards. So you haven't actually reduced technical debt.
No, you've just outsourced the creation of new, non-compliant code to an AI that doesn't know the house rules.
That's the perfect way to put it. It acts like a supremely competent intern who is completely unaware of the last decade of really important organizational decisions.
That analogy lands perfectly. It really highlights the strategic roadblock. So this problem needs a strategic fix, and this is where it gets really interesting for me. The sources point to a massive architectural pivot they're calling prompt as configuration.
This is the core conceptual shift we really need to absorb today. Platforms like GitHub have introduced these very specific configuration files. We're talking about .github copilot-instructions.md and agent.md.
And these are now new essential artifacts in modern software engineering.
They are. And crucially, these files are not passive documentation that someone might read. They represent a proactive governance layer.
And that word, proactive, that's the real game changer here. I mean, think about traditional quality assurance. You have your continuous integration checks, your CI, vulnerability scanners, linters.
But they'll all react.
They're all fundamentally reactive. They catch deviations after the code has already been written, committed, and usually pushed up. And then you pay the cost of context switching, going back and fixing the mistake.
But these instruction files, they shape the generative process itself. By injecting the organizational rules directly into the AI system prompt, they preempt the deviation before a single line of bad code is even written.
So you're transforming the AI from this general knowledge engine into a context-aware specialist.
One that inherently understands the corporate constitution, as you said.
Okay, so our goal for you, the learner listening in, is to understand exactly how this constitutional architecture works, how these static configuration files become dynamic, executable rules in the actual workflow.
And then what the profound practical implications are for the day-to-day lives of the three key personas in any modern software team. That's the software engineer, the DevOps engineer, and of course the security engineer.
Right. And to really grasp the magnitude of this shift, I think we have to start by looking under the hood at the technical architecture. How does this context injection actually work?
Yeah, let's do it. The research is clear that overcoming that initial statelessness was the first major hurdle. How do you move beyond the AI, only seeing the file you have open at that exact moment?
How do you make it repository aware?
That's the term. And the underlying mechanism is all about systematically injecting repository-specific knowledge, so the content of these new instruction files, directly into the LLM's prompt payload. And this happens every single time a developer initiates a query or asks for a code completion.
And what's so crucial here, and what the sources really hammer home, is that this injection isn't just a flat list of rules. It follows a very specific, prioritized hierarchy.
Hierarchy of context, yeah.
It's like the AI is being forced to consult a ranked list of corporate law before it's allowed to make any suggestion at all.
That prioritization is the strategic bedrock of this entire system. If you look at Table 1 from the sources, it details these strict priority levels that dictate how the AI weighs conflicting pieces of information.
And at the very top, priority 1, you have the system metaprompt.
Right. These are the universal, immutable safety and ethical guardrails set by the model provider, like OpenAI or GitHub. You can't overwrite these. They are hard-coded.
Okay, but right beneath that, at priority 2, that's where you find the repository instructions, our new markdown files.
Yes. This is the constitution of the project, and it holds precedence over pretty much everything else.
And then below that, you start getting into the more general stuff.
Exactly. Below that, priority 3 is user custom instructions, which are just personal preferences. Always use emojis in your responses or something like that.
Trivial stuff.
Then priority 4 is the immediate active context, the open file, your cursor history, recently viewed files. And then way, way down at the bottom, at priority 5, that's where you find the fundamental global training data, the massive pool of generalized knowledge from the internet.
So let's go back to our opening example. If the base model, priority 5, suggests using Axios, but the repository instructions at priority 2 explicitly mandate the custom fetch wrapper.
The instruction at priority 2 wins. It wins every single time. It's not even a contest.
And that priority reversal is the massive strategic insight that the sources are flagging here. Repository instructions override general training data.
Yes. And think about the economic implications of that for a minute. Historically, if an organization wanted to align a huge foundational model, like a 70 billion parameter model with their unique proprietary standards, what would they have to do?
It would cost millions. You'd have to do traditional fine-tuning.
Millions of dollars, months of gathering domain-specific data, dedicating massive computational resources. I mean, it's a huge undertaking.
A process that is just completely prohibitive for 99% of development teams out there.
Correct. But by using this text-based instruction injection, an organization can instantly fine-tune the AI's behavior for their specific domain, their stack, their libraries, their security rules, in 30 seconds.
You're just writing a markdown file.
You're applying a cheap, fast, text-based patch to the model's behavior. You're customizing the application layer without ever touching the foundational LLM. This is a profound shift in cost efficiency and speed of deployment.
It effectively lowers the barrier to entry for custom AI behavior from you must be a massive tech giant like Google or Meta to you must be able to write a good markdown file.
That's it.
So let's look closer at that primary interface, the copilot-instructions.md file itself. What governs its content? What are the rules?
So this file is the main interface for customizing the standard conversational experience of Copilot chat. It lives, predictably in the repository's default branch, usually inside the .github folder.
So it's version controlled, just like any other critical piece of code.
Exactly. But there's a catch. The LLM's inherent context window limitation, what we call token budgeting, it imposes a really critical constraint.
Right. You can't just copy and paste your 200-page internal engineering manual into this file and call it a day.
Not at all. The input is typically hard limited. We're talking around 2,000 to maybe 4,000 characters.
That's not a lot of space.
It's not. And this technical limitation forces a crucial and I think a really healthy trade-off onto engineering leadership. They have to prioritize.
You can't afford to waste space on low-value instructions.
No. Things like minor formatting details that a traditional linter could handle anyway. That's out. You have to focus exclusively on the high-value items, the security non-negotiables, the mandatory architectural patterns, the required external dependencies. It forces teams to actually sit down and define their true constitutional rules.
That sounds less like a technical constraint and more like a mechanism to enforce clear thinking about what truly matters in your code base.
That's the unintended but very real benefit. And what makes this system actually succeed from a developer adoption standpoint is that the ingestion is entirely passive. It's silent.
The developer doesn't have to do anything.
Nothing. They don't need to remember to prime the AI or copy-paste a list of rules or click a button to load the context. The instructions are just silently appended to the system message of every single chat interaction. It removes all the friction, and that guarantees high adherence.
Okay, now, the sources hint at an evolution beyond just chat assistants. They're moving into these active agents that can perform multi-step tasks all on their own. This introduces the key distinction of a second file, agent.md. How do we differentiate between the chat instructions and the agent instructions?
This is a critical point because the industry is rapidly moving toward these agents. These are AI systems designed to plan, to perform research, and to execute complex, multi-step tasks across an entire code base.
Things like what we're seeing in environments like Copilot Workspace.
Exactly, and that requires a very different type of instruction.
So if copilot-instructions.md is all about style and generation advice, what the code should look like, what purpose does agent.md serve?
The distinction is vital for safety and for functionality. So copilot-instructions.md guides conversation and code style. An example would be use TypeScript interfaces, not types, for clarity. That's a style guideline for the output.
Okay.
Agent.md, on the other hand, it focuses on repository topology, execution safety, and mandatory workflow.
So it's less about the grammar of the code and more about the geography of the repository.
That's a perfect analogy. The agent.md acts as the agent's map and its operational handbook. It guides execution. For example, it might say, the primary front-end source code is located in the web directory. Or run npm test before executing npm build in all CI contexts. And critically, something like, do not edit files in the legacy v1 appy folder under any circumstance. Those changes must go through the dedicated retirement process.
So you're giving the agent the equivalent of a senior engineer's tribal knowledge. Where all the bodies are buried, which parts of the system are too fragile to touch, and the exact sequence of commands needed for a safe deployment.
It governs execution safety and dependency management. It's essential for making sure that when an agent attempts a complex task, it operates within known, approved boundaries. And this distinction becomes absolutely critical as we move into part 2, how these static documents actually jump off the page and become active, executable rules throughout the entire software development lifecycle.
Let's talk about those triggers then. We've established these rules live as configuration files in Git, but how does this constitutional code base actually come to life? How does it start dictating actions in a developer's day-to-day work?
Right, so we can basically categorize the mechanisms into 2 buckets, passive ingestion and active invocation. The passive method is the simplest and right now the most widely adopted trigger.
And that's the always-on pair programmer experience we've been talking about. It starts the second you launch Copilot Chat inside your IDE, VS Code, JetBrains, whatever you're using.
That's right. The extension scans for that instruction file immediately when the workspace loads. So the experience of just starting a chat session is drastically different for the developer.
Okay, so without instructions, a junior developer asks, how do I create a new API endpoint? What do they get?
They'll get a single generic code block. It will probably use a popular but possibly disallowed framework structure. It's the most common answer, not the right one.
But with the instructions loaded, the AI knows the rules. It knows something like, all API endpoints must adhere to the standardized service controller repository pattern.
And so the response is fundamentally transformed. Instead of just one code block, the AI automatically generates 3 separate architecturally compliant files. You get the controller to handle the HTTP request, the service method with the business logic, and the repository query that talks to the database.
And it puts them in the right folders, presumably.
Critically, it places each one in its correct functional file structure. This is so far beyond mere code generation. It's automated architectural reinforcement.
That's a massive productivity gain, especially for large teams or, for new hires just trying to get up to speed. It effectively automates the first 30 minutes of setup ceremony for any new feature.
It's an automated onboarding buddy. It reinforces these complex, multi-file architectural standards without ever needing the intervention of a human senior engineer for that initial scaffold.
Okay, so that's the passive side. But the sources suggest the true power really emerges with the active invocation of these rules, particularly when you integrate them with GitHub issues through something like Copilot Workspace.
This is where the instruction set transitions from being just advice to being a formal, executable specification for agentic labor. Let's just trace that crucial issue to PR workflow.
Okay, so a human engineer defines the intent in an issue, something like refactor the login logic to use OAuth 2. They don't write the code, they just click Open in Copilot Workspace.
That click, that's the trigger. The agent system initializes. First, it reads the issue to understand the goal. Second, and most importantly, it consults the agent.md file to understand its operational boundaries and constraints.
So it's doing a pre-flight check.
It's performing immediate constraint checks. Is there a security requirement? If the instruction mandates, all OAuth implementations must use the vetted corporate passport.js wrapper, the agent immediately incorporates that dependency into its plan.
What if a file's off limits?
If another instruction says the file coreauth.ts is frozen and cannot be modified until Q3, the agent sees that safety lock and adheres to it. It won't touch that file.
So the agent executes a plan for the refactor, generates all the required changes, and then scaffolds a pull request.
Yeah.
All while adhering to these constitutional rules. The style rules from chat instructions and the execution boundaries from the agent instructions.
It is policy directly dictating automated labor.
Wow.
And this adherence can get incredibly granular through what the sources call the task list trigger. Developers can trigger these tiny micro-agentic tasks directly inside an issue or a PR just using a specific syntax, like typing at Copilot update the dependency versions for React.
And the system sees that at Copilot handle, pulls in all the relevant constitutional context, and then just executes that one specific task.
Yes, and here's a critical security and consistency win from that. Let's say the instruction states, always pin dependencies to exact version numbers.
Okay.
The agent doesn't just bump the version. It specifically updates the package.json entry to remove those potentially dangerous carets or tildes.
Because those symbols can pull in newer, untested versions.
Exactly. They allow for non-deterministic dependency installations, which can introduce unexpected breaking changes or even new vulnerabilities. The constitutional rule dictates the execution outcome, ensuring security by default.
Okay, so we have the interactive chat, we have the active workspace.
Yeah.
The sources reveal a fascinating third trigger, leveraging instructions for automated code review inside CI/CD. This is how we get to what they call the semantic linter.
This is a really clever use of the technology. It typically involves configuring a dedicated GitHub action to run whenever a pull request is opened. The mechanism is a perfect example of leveraging the LLM's strengths. The action sends the PR diff, the code changes, to an LLM API.
But it injects the entire copilot-instructions.md file as the system prompt before the code diff.
That's the key. The prompt acts as the job description. It's essentially saying, act as a senior code reviewer and security architect. Your sole task is to check the attached code changes specifically against the policy contained in the following instructions.
And the result is a semantic linter that just operates on a completely different plane than traditional tools.
A completely different plane. Traditional linters are fantastic at catching literal syntax errors or formatting, spaces instead of tabs. They rely on abstract syntax trees, ASTs, to check code structure.
But they can't catch intent.
No. But the AI reviewer, guided by these instructions, it catches intent and architectural alignment.
So it can flag a violation that a human reviewer might easily miss, or one that a standard linter just isn't programmed to even look for.
Precisely. It can leave a comment directly on the PR that says something like, violation of instruction, #9, PII masking. The function log user data is logging unmasked email addresses. Please use the mask PII utility as mandated by the repository constitution. It elevates automated quality assurance from just structural checks to actual philosophical compliance.
That is a seriously powerful operationalization of institutional knowledge. So now that we understand the architecture and the triggers, let's dive into the practical applications for the people on the ground. Let's start with the software engineer.
Yeah, for the core developer persona, I think the primary value of the instruction set is this dual benefit of reducing their cognitive load and automating what the sources perfectly term the ceremony of development.
Ceremony. Meaning all that repetitive boilerplate you have to write just to satisfy the framework or the organizational standards before you can even start writing the actual logic.
That's it exactly. Let's start with framework standardization and boilerplate reduction. I mean, think about creating a simple UI component, say a button, in a modern, large-scale enterprise React application.
You don't just need one file.
Oh, no. You don't just need the component file itself, the button.tsx. To satisfy modern standards, you often need a CSS module, so button.module.css, a just test file, button.test.tsx, a storybook story for documentation, button.stories.tsx, and a clean export file, an index.ts. That's 5 files for one button.
And if a developer has to manually create those 5 files in all the folders, they're spending, what, 15 minutes on setup before they even write a single line of business logic? That time adds up incredibly fast.
But the constitutional instruction captures that standard. It says, when generating React components, always create a folder containing the component, a .test.tsx file using React testing library, a .module.css file, and a storybook story. Use functional components with typed props.
So the engineer just types, create a button component.
And Copilot generates the code for all 5 files, perfectly conforming to the required folder structure, naming conventions, and internal style guides.
That moves the value line. That's what you're doing.
Right.
Engineers stop spending time on file structure and manual scaffolding, which is low-value, repetitive labor, and they can immediately focus their energy on the actual high-value business logic.
The impact on testing philosophy enforcement is also immense.
No.
Testing is notoriously difficult to standardize across a large team.
Oh, for sure. Teams often drift into brittle practices, like using excessive mocking to isolate units.
Which leads to tests that break every single time the underlying implementation changes, even slightly.
It's a massive maintenance headache. So how does the instruction set solve for that?
By embedding these rigorous, unyielding standards. An instruction might read, testing strategy. Do not mock the database driver. Use the test container instance provided in global.ts for all integration tests. All test logic must strictly follow the arrange act assert pattern.
So the AI reads that, and when it's prompted to write tests for this new service, what does the output look like?
The generated test code automatically imports the correct test container instance and scaffolds the test file in that AAA format. This ensures consistency and validity across the entire test suite. It prevents brittle tests by design.
And finally, documentation, the thing that is always the first to suffer during a tight deadline. The sources highlight documentation as code enforcement.
Right. Documentation is only valuable if it's consistently applied and, up to date. If the instruction mandates, strictly follow the JSDoc standard for all public methods. Always include at param, at returns, and a detailed at example block for every function.
Then when a developer highlights a function and just asks Copilot to document this, what happens?
The output is a fully formatted, API-compliant documentation block. High-quality, consistent documentation is maintained with what the sources truly call near-zero effort.
That's a huge win for long-term maintainability and knowledge transfer. Okay, let's pivot. Let's talk about the DevOps and infrastructure persona. For them, the repository is the infrastructure, so precision and compliance are absolutely paramount.
Indeed. For DevOps teams, these instructions transform into critical guardrails for infrastructure as code, or IAC. We're talking about true shift-left compliance-catching policy violations at the generation stage, not at the deployment stage, which is far, far too late.
We've all seen it. A developer writes some Terraform or CloudFormation, they forget a critical security flag, and then hours later the deployment pipeline rejects the code. It's just wasted compute time and wasted human time.
And the instructions prevent this policy drift right at the source. Take policy as code enforcement using something like Terraform or OpenTofu. The instruction set can mandate several organizational non-negotiables. For instance, 1. All S3 buckets must have server-side encryption configuration enabled and enforced. 2. All resource blocks must include the required tags, environment, owner, and cost center. 3. Never deploy any resource into the default VTC.
So if the engineer just prompts, give me Terraform for a private S3 bucket, the AI doesn't just give them a basic bucket.
No, it generates the basic bucket resource, but it automatically embeds those 3 mandated compliance settings. It generates the necessary encryption blocks and placeholder tags by default.
So the policy is enforced not by a later security scanner rejecting it, but by the agent automating it from the start.
The code is compliant while it is being written. That dramatically speeds up the delivery pipeline and reduces those non-compliance errors that just waste everyone's time in code review.
That level of enforcement translates perfectly to Kubernetes manifest consistency, which, I mean, those files can be incredibly verbose, and it's often where teams fail to embed production readiness practices.
Kubernetes YAML can be so fragile, and it often misses crucial operational elements. The instruction set can enforce strict production-ready rules like always define resources.requests and resources.limits for every container to prevent resource starvation.
Right.
Or use liveness probe and readiness probe on all deployments to ensure proper self-healing. Image tags must be pinned to immutable SHA hashes, never using the insecure latest tag.
That rule about SHA hashes is a huge security best practice, but it's often really difficult to enforce manually.
That's right. The AI ensures the generated YAML structure requires that secure configuration, and crucially, it avoids generating that common insecure image, myapp.latest entry, because the instruction explicitly forbade it. The resulting YAML is production hardened by design, immediately mitigating common operational failures.
And finally, what about CI/CD pipeline security? That's a huge risk area, especially when workflows have elevated permissions.
The principle of least privilege is paramount there. The instruction can enforce a secure default state, something like workflow permissions should be set to contents, read by default. Permissions should only be elevated for specific, isolated deployment jobs.
So when a developer asks for a simple CI script to run unit tests,
The generated YAML automatically includes the secure permissions, contents, read block at the top. It mitigates a major attack vector that starts with overly permissive workflow definitions. The AI starts secure by default, and the human has to consciously and explicitly override it.
this brings us naturally to the security engineer persona, who is, I think, perhaps the biggest beneficiary of this constitutional code base. They can finally scale their expertise across every single line of code being written instead of relying on reactive audits after the fact.
Absolutely. Security teams are perpetually outnumbered. They're often seen as the bottleneck for feature velocity. Embedding their accumulated wisdom directly into the AI is, I think, the holy grail of scalable, proactive security governance.
So let's start with vulnerability prevention, essentially creating an anti-pattern list that's specific to the organization's tech stack.
Security teams know their stack's known weaknesses. They know the specific ways their databases are usually exploited or how their front-end framework tends to leak memory, so they codify these anti-patterns directly into the instructions.
So for the classic SQL injection vulnerability.
The instruction would read, never, under any circumstance, use string concatenation for building SQL queries. Always use the parameterized function db.execute query params.
So if a developer tries to generate a raw query with variable insertion, the AI doesn't just warn them.
It actively refuses the vulnerable approach. It pivots to the parameterized, secure version immediately. It creates a self-correcting coding environment.
That's powerful.
And similarly for front-end security. When rendering user input in React, never use dangerously set in your HTML. Furthermore, input validation must occur exclusively in the API layer using the Joy validation library. This instruction enforces a secure architectural separation of concerns, preventing accidental XSS vulnerabilities right at the point of code generation.
Which means the AI is a real-time security mentor. It's preventing the vulnerability before it even gets into the PR stage, and that drastically reduces the defect cost curve.
We also see the AI acting as a crucial data privacy advocate, particularly around secret management and PII. Accidentally committing secrets or logging sensitive user data are persistent catastrophic errors.
So the constitutional instruction can be straightforward but incredibly powerful. Something like, never hard code API keys or connection strings. Always use process.env or the organization's dedicated secret manager utility.
And then add, if code involves PII, personally identifiable information like an email or phone number, wrap the logging statement in the approved mask PII utility.
So if a developer writes code to log a user object for debugging,
the AI suggests, and often automatically includes, the masking wrapper. So you get logger.info, user accessed endpoint, mask PII user. It's not just flagging an error, it's providing the precise, approved, and compliant mitigation technique automatically. It prevents data leaks in application logs across the board.
And finally, fixing vulnerabilities in dependencies remediation. That is one of the most tedious and risky jobs. The source material emphasizes how these instructions can guide remediation agents.
This is a really complex, multi-step workflow. Imagine a security alert surfaces for an outdated library, say a critical vulnerability in Lodash. The instruction guides the agent's complex behavior for the fix.
How so?
The rule could be, when fixing dependencies, always check the OSV scanner results for severity. If upgrading a core library, always check the changelog.md for breaking changes first.
That's a huge leap forward. So the agent, following this sophisticated set of rules, doesn't just blindly bump the dependency version from 4.1 to 4.5. It executes a pre-flight checklist.
Right. The agent ensures the security fix is stable and architecturally sound. It actively checks the changelog for breaking changes before committing the update. It prevents that classic scenario where a security fix inadvertently breaks the build or introduces a new functional bug because the new library version changed an API parameter. The AI manages both security compliance and stability in one go.
We've covered the architecture, the triggers, and the deep impact on all the engineering roles. Let's pivot now to the meta skill required to actually manage this system. Writing effective instructions is clearly a new competency, which the sources are calling instruction engineering, or prompt ops.
This is truly the new engineering discipline emerging from the shift. I mean, these instructions are configuration. And just like any YAML or code configuration, they have to be clean, they have to be efficient, and they have to be optimized for the system they are controlling. We're dealing with the subtle and often fickle attention mechanism of the LLM.
The sources provide a great list of structure and formatting best practices in Table 2. Let's detail how this formatting directly impacts how well the AI adheres to the rules.
Formatting is everything. It really is. It aids the model's segmentation and weighting of the constraints. First, the use of H2 headers, so #tag coding style or #tag security non-negotiables or #tag infrastructure mandates. This helps the model mentally segment the logic.
So if a developer asks a question about styling, the model can focus its attention just on the rules under that specific header.
Exactly. It helps it use its limited context window more efficiently. Second, and this is critical, is the use of few-shot examples. So you write, do this, and then an example of compliant code, don't do this, and an example of non-compliant code.
Because LLMs learn by pattern matching.
Incredibly well. Showing the desired outcome is vastly more effective than trying to describe it in abstract terms. It just removes all the ambiguity and ensures the model produces the exact syntax and style the organization prefers.
And crucially, brevity and structure. We know the context window is limited, so the sources advise keeping instructions well under the hard maximum, maybe below 2 KB, and using bullet points wherever you can.
That structure is vital. When an LLM processes bullet points, it often treats each bullet as a distinct, weighted constraint in its attention mechanism. It gives it more emphasis than just a dense paragraph. And always use an imperative and direct tone. Always use X, never do Y. That tone helps avoid the ambiguity that leads to model hallucination or deviation.
Speaking of ambiguity, let's discuss the negative constraint paradox. This is a subtle but really profound piece of prompt ops wisdom from the sources.
It is. It stems from the inherent weakness of only telling the AI what not to do. So if you only write, do not use var in JavaScript, the model understands that var is bad. Okay, great.
But it still has to generate something.
It still has to generate a functional output, so it has to choose a positive alternative. It might choose let, even if your standard actually mandates const for most things.
So the recommendation is to always pair the constraint with a positive alternative.
Always. Instead of that weak, purely negative constraint, you write, do not use var. Always use const for immutable variables, and let only for counters or variables requiring reassignment. By providing the positive sanctioned path, you drastically reduce the model's search space and the probability of it making an error. You are not just forbidding, you are proactively redirecting its generative efforts toward compliance.
This implies that these instruction files have to be treated exactly like application code. They need maintenance and versioning.
Absolutely. They must live in Git. They must be reviewed via pull requests, maybe even requiring a senior engineer or a security architect to sign off before merging. And they require iterative refinement, a continuous feedback loop.
So if the team sees Copilot making the same architectural mistake twice,
the immediate response shouldn't be to blame the tool. It should be to update the instruction set to clarify the rule or to improve the few-shot example that you're providing it.
And the sources even suggest a future state of modularization, where these instruction sets are composed and imported. So you might be able to import a validated internal at company security instructions module into your specific repository's configuration.
That's the logical next step for scaling this expertise across hundreds or thousands of repositories. And finally, we just need to touch on the concept of the persona definition.
This is where you tell the AI exactly who it is. You're setting its risk tolerance and its priorities.
Right. Defining the AI's role sets the tone, the style, and the inherent robustness of its generated code and its advice. For example, you are a senior system architect focused exclusively on high availability and fault tolerance. You assume all network calls will fail and prioritize defensive code and idempotency.
By priming the model with that level of risk aversion, it's going to automatically shift its output style.
The model adopts a conservative, robust style. It will prompt itself to automatically include sophisticated elements like try-catch blocks around every single I/O operation, automatic retry logic with exponential backoff, and explicit timeouts in the code it generates, rather than just delivering the simple sunny day path. It adjusts the model's inherent risk profile to match the company culture and operational requirements.
This has been a truly comprehensive deep dive into the operationalization of AI governance. Let's try to synthesize the monumental impact this shift represents by looking back at Table 3, the impact analysis matrix provided in the sources.
Yeah, the comparison between the standard generic LLM output and the instructed context-aware output is just striking across all these different dimensions of business value. Take data handling. The standard AI, it generates a basic database model class.
Right.
The instructed AI generates that class plus mandatory validation decorators and automated audit log fields. The immediate business value there is enhanced data integrity.
Or what about robustness? When you're writing an API client, the standard response uses a simple, unhandled fetch with no timeouts.
But the instructed response uses the custom organization-approved API wrapper with automatic retry logic and standardized error reporting. That builds significant resilience into the application by default.
And critically, when a new team member needs an explanation of the code, the standard AI provides a general summary of the syntax.
Whereas the instructed AI provides an explanation that specifically maps the logic to business domain terms and architectural patterns that are used in the instructions. This drastically accelerates onboarding speed and knowledge transfer.
So what does this all really mean for us? The introduction of copilot-instructions.md and agent.md marks a pivotal moment. It's shifting us decisively from a reliance on generic intelligence to the practical daily application of contextual intelligence.
It democratizes and scales institutional knowledge across the entire engineering organization. For the software engineer, it means automated compliance and freedom from that boilerplate fatigue. For the DevOps engineer, it means reliability and policy are baked into ISC right at the source. And for the security engineer, it provides the scalable, proactive governance they have been desperately searching for.
So our three key takeaways for you, the learner, before you start implementing this in your own work are these. First, remember that instructions are constitution, not documentation. They are active, executable rules that shape code generation, not just passive notes you hope someone remembers to read.
Second, understand that agents require maps. The agent.md file is essential for any autonomous workflow to understand repository topology and execution boundaries. You simply cannot deploy multi-step agents safely without providing that context.
And third, embrace shift left via prompting. Whether it's security, infrastructure, or style, policies are enforced at the very generation step before the code is even half written. And that drastically reduces the cost of fixing defects later in the software development lifecycle.
The sources are unanimous in their prediction that these instruction sets will eventually be shared and forked and managed just like open source libraries, creating codified standards for engineering wisdom across the entire industry.
And that potent idea leads us to our final provocative thought for you to chew on. If these instruction files become the absolute non-negotiable, something to ponder as you start defining your own digital constitution. Thank you for diving deep with us. We'll see you next time.